I'm Sergio Farragut. I work for the developer relations team. I'm a developer advocate and here at Imply, and I'm going to talk about the Druid multi-stage query framework in this recording. So we're going to talk about the proposal for the multi-stage query framework. This is a proposal to add to the open source project, and we'll talk about that. We're going to talk about its current implementation, its current architecture within the existing Druid architecture, and then what it enables, which is the SQL Based Ingestion and all of the SQL elements that it enables, the syntax that it uses to use SQL to produce all of the same capabilities that the traditional Druid batch ingestion has. And finally, we'll go into the details of each of the kinds of stages that it uses to run these operations, and let's get going. So the proposal. So the proposal is in the Apache Druid project in the issue listed here, 11.9.29, and it's called Batch Ingestion using SQL Insert. So the summary is that it enables batch ingestion using SQL. So you can specify dimensions and metrics using SQL expressions and all of the richness of the SQL language for transforming and converting the data into the form that you need for ingestion. It allows you to specify both segment granularity and secondary partitioning through SQL syntax. It also allows you to specify query granularity using any arbitrary timestamp expression in SQL, as well as enabling roll-up or aggregation, summarization of the data using traditional SQL group by. It enables access directly in the SQL to external sources of data using an external table function. And so finally, it enables overall, it enables complex ETL pipelines from batch sources with all the expressibility of SQL. We expect it to be released in the Apache Druid 0.24 release. So the motivation is ease of use, right? It's about converting what used to be ingestion specs specified in JSON, which are pretty verbose and require a lot of sections of the JSON data structure to be specified. So it's more complex to write and even to read than the traditional SQL statements, which is what we have on the right. These are actually equivalent ingestions. One is specified in JSON, and the other just using SQL in a few lines of code. So the architecture. This it uses the existing. So the initial implementation uses the existing execution model in Druid. It uses the broker, the overlord, and the middle manager's worker slots to enable the operation. The way it works is the users submit a SQL query through a new API. It's the V2 SQL task API. The broker translates the SQL and into a native query representation. It submits the request to the overlord, retrieves a task ID from the overlord, and returns that task ID back to the user. This is an asynchronous ingestion operation, so you interact with it as a user using that task ID. The overlord takes that request, creates the task ID and returns it. It spawns tasks in the middle managers, and it provides status of the job asynchronously as the job evolves. So in the middle managers, the overlord spawns these tasks using existing worker slots. One thing to note here is that as part of the request, the SQL request, you specify context parameters for the operation. And one of those parameters is the MSQ num tasks, which defines how many workers are going to be involved in this particular operation. So within each request, you can specify the level of parallelism. But one important thing to note is that that is the number of query workers. You'll always have to have one more worker slot for the query controller that also occupies a worker slot. So you'll need the number of tasks that you want, plus one worker slots to start one of these jobs. And they need to be all available in order to start the job. Once they start, the query controller coordinates the execution of the job across multiple stages with all of the query workers as the job evolves. So how does that work? So like we said, the query controller has a plan, right? It has the set of stages that it's going to run through, and it communicates with the query workers to execute each of those tasks. The query workers execute the tasks and then reshuffle the data. If you look at the arrows, we've labeled them. P1 is in creating a partition 1, P2 and P3. There'll be as many partitions as there are workers, because you're redistributing the data among the workers. So if you notice here, so each execution and shuffle the shuffle part will generate 3 partitions in this case because we have 3 workers, and they're labeled P11. This is created by 1, so partition 2 created by worker 1 and partition 3 created by 1. We just labeled them in this slide like this to just explain the process, right? And if you follow all the arrows, you'll notice that in the end, all of the P1s generated by the workers end up in worker 1, P2s in worker 2, and P3s in worker 4. So this enables the possibility of reorganizing the data between stages and then executing the next stage, and that's necessary for certain operations, as we'll see, and that's really the innovation in this in the multi-stage query processing, in that they can execute a stage, reorganize the data, execute another stage, reorganize the data, and so forth as it needs in order to resolve the whole ingestion process. So what are those stages? The first stage is the scan. The scan is capable of reading from input files. So this is where the external function comes into play, and it accesses those external files. It runs them in parallel across the workers and applies operations like filtering, projection, broadcast joins, even ordering. And it can apply limits only if the limit is without an order by. You'll see there's another limit operation that requires that the data be sorted in order to do that. So the next one is a group by pre-shuffle. So in general, distributed aggregation, because the data isn't all organized originally as it needs to be to do a full aggregation. All of the same values that you're grouping by need to be together to be able to do that aggregation. And in the input files, the organization of the inputs is arbitrary, right? So that first stage does the initial or partial group by of the values that are within the inputs that each worker receives. It does that local aggregation, and then proceeds to reorganizes the data so that all of the group by values are together, and proceeds to the next stage, which is the group by post shuffle. In this stage, the data is known to be already organized by the grouping keys, and so the final aggregation can be executed, and some ordering can also be done in this stage. One thing I forgot to mention is both the scan and the group by pre-shuffle can read from source files. The limit operation is where you have a limit and or not offset and limit in the SQL, and you have some kind of global order by, so that in this stage all of the data will be gathered into a single worker, ordered, and then the offset and limit applied to the results. And finally, the segment generator. This is what creates from the data that's been reorganized. It creates segment files and partitions and publishes those to deep storage. So let's talk about what it enables, the SQL-based ingestion. So first of all, there's the new API, right? This is at the Druid v2 SQL task. The payload for that API is a JSON structure that includes the query and the context for that query. So the query is any of the insert or select operations that multi-stage query enables. And the context specifies a list of parameters that control how it executes. The most important one, like we said before, is MSQ num tasks. And just a reminder that if you specify 3, that means 3 workers, and you'll need another worker slot for the controller. It responds with the task ID and the current state of the job. You use that task ID to interact with the query using these other APIs where you where you can obtain the query payload, check its status, get a report once it's done, or even retrieve results if you're doing a select operation. And this is how you retrieve results asynchronously. Or finally, just cancel the query with the shutdown API. So the 3 SQL statements that it enables are insert into a target data source, replace of a section of a source, and so you're replacing. You can replace the whole thing, or you can replace a particular time chunk within or particular time interval within the data source by specifying the overwrite where condition and specifying a condition that defines a time frame using the __ time column. And finally, just individual selects, where you can actually do a select of external sources and just query external sources with the intent really of testing the ingestion SQL that you're going to do. And you would probably want to add a limit to it. You don't want to process the whole thing without actually doing the ingestion. But so the select is so that you can test the transformations that you're executing before you actually do the insert or the replace. So the extern function, all right? This is this goes in the from clause. It's an external table function, and so it's specified as from table extern and a set of parameters to the extern function that specify the Druid input source. These are all the same input sources, batch input sources that are available in the traditional ingestion spec for Druid. The input format, which is also the traditional input formats that are available, and then a list of or an array of column specifications that specify the schema of the input source that we're going to be reading from. So in Druid, those of you who know Druid already know this, but for those of you who don't, I'll just describe in general. The ingestion process can take arbitrary files that may have arbitrary ORing in them. This is an example where the timestamps are distributed all over the place and the rest of the dimension values are also kind of randomized. To make the point that the ingestion will first segment the data into time chunks, right? And the size of those time chunks is defined by the segment granularity in original ingestion spec nomenclature, or now in SQL it's specified with the partition by clause, where you can say partition by minute, partition by second, by day, by week, etc., by any time frame that's supported. In this case we're doing by day, so we see that in the result we have each time chunk corresponds to a whole day. So the data is redistributed as it's ingested into these segments that each represent one day in this case. And once the ingestion completes, the data is sorted on time within each of those time intervals, and sorted by the other dimensions in the data set. So that's what the colors here are meant to represent, from dark to light, that sorting that occurs in the ingestion. Additionally, you can in Druid, you can split up time chunks or segments within time chunks into separate partitions based on other dimension columns, and this is called secondary partitioning, or secondary range partitioning to be specific, that allows multiple columns to be used, multiple dimensions to be used to create these equally sized or roughly equally sized splits of the data. So that's now specified in SQL using the clustered by and a list of dimensions. So our first SQL. This is a non-roll-up ingestion. So this is going to insert into the data source called target table in this case, that if it doesn't exist, it's going to get created. If it does exist, it's an append operation. We're adding this data to whatever data is already there. You need to specify the time dimension. So this is done essentially by taking by specifying an expression that will result in a timestamp. And naming it __time. That assigns the primary time dimension, and that's how the data will be partitioned into time chunks. The rest of the expressions are the rest of the columns, the columns that will be created in the target data source. And it can be any arbitrary SQL expression using the input fields from the extern table function that we talked about before. So the where clause can be used for filtering, and so this is any arbitrary condition on the or set of conditions or complex conditions on the input fields. On an insert or a replace, you will need to specify the partition by that determines the size of the time chunks, and you can optionally specify the clustered by, which does that secondary partitioning within the time chunks. So the Druid also is capable of ingesting data and summarizing data as it ingests it, and this is traditionally in traditional ingestion called a rollup. So it's enabling rollup for the ingestion, and now it's enabled by using SQL group by, which is the natural way to aggregate data in SQL. The time can also be transformed as part of the ingestion. This is an example where we're transforming timestamps that include hour and minute into just days. So we're using the floor function to transform the event time from the input and truncate it to a day, right? And that helps us do summarization of the source data and therefore reduce the data volume and calculate some aggregates ahead of time. And we enable rollup using the group by clause in SQL, where we will need to specify the time column and any of the other dimensions that are present in the select expressions that are not aggregate functions. So this is an example of such an aggregation, or such an summarizing ingestion, a rollup ingestion. So again, we have insert or replace into the data source, but now the select is an aggregation select that includes the group by, again, by the time dimension and by the all the other dimensions that are expressions in the select portion. So the select includes the time expression, where you can use floor or ceiling, or really any time function that results in a timestamp that transforms the time in some form to produce that target time dimension that we're looking for. Then followed by the dimensions, which again can be arbitrary expressions. You can take the input field directly or do some transformation on them, like the upper that we're doing here on the user field. And finally, the aggregate metrics. So these are the sum, min, max, average, all the traditional aggregate functions in SQL, and also the approximation functions that Druid has that allow you to use theta sketches or things like hyperlog for distinct counts, or quantile functions that store an aggregate representation of the data that can then be reaggregated on at query time. And finally, the partition by and cluster by are the same. You'll need to specify the partition by for defining the time chunks and the size of the time chunks, and optionally the cluster by to subpartition that the result of the aggregation. You can also use lookups during the ingestion. So we can specify multiple with clauses, where in this case we're specifying langs is a lookup source for languages in this example, and wiki is a lookup source for the event data that we're ingesting. You can have multiple lookups. One thing to understand about lookups here is that lookups will be read and broadcast, so copied into all of the workers. So all of the worker tasks will need to have enough memory to store a full copy of each of the lookups that you specify. And then the workers will process their own portion of the event source and do the joins to the lookups as it does so. You can specify the reference to the lookup like you would in SQL, first using a join, right, where we're joining the event source to the lookups using some field in the event source and the ID field in the key lookup that is the lookup table, and then using the reference to the lookup with clause, so langs in this case, and another field in that lookup to do that transformation into the lookup value. This is equivalent to what we used to do in the transform spec lookup function in the traditional ingestion specification. I believe one thing I didn't mention, so the source events. So again, I don't know if I've mentioned this enough, but as you decide on your external source, the number of files in the source will determine your max parallelism along with your workers. So if you have 3 workers and only 1 file, only one of those workers will be able to read the file because there's just 1 file, and then it'll redistribute it for the next stage. But if you want that first stage to have significant parallelism, you need at least the number of files as you have workers. So anyway, that's something to take into account. So now let's dig into each of the individual stages and what they do in order to resolve queries or ingestions. So the scan stage is capable of reading files, so it will the controller will distribute whatever set of input sources there are among the workers. The workers will open those files, read them in, and apply. They can apply filtering. They can apply projections, selection of a subset of the columns. They can broadcast. So in preparation for a lookup, the broadcast operation is that copying to all the other workers, and it can, in some limited cases, apply a limit only if there is no order by in the query. And then it redistributes the data in preparation for the next stage. And the group by pre-shuffle stage is similar to scan in that it can read input files, so it does the same. It's the same from that perspective. It can also do filtering and projection, but what it does that's special is the local aggregation. So like we said before, input files have some arbitrary order. We have no control of what the input files are, and so because it has an arbitrary order, you first need to execute the local aggregation, the local summarization. That means that summarize only with the input files that each worker read from, but there could be values that are also being aggregated in another worker, right? So the same resulting time and the same dimension values could exist in other input files, and therefore those local aggregations are really partial aggregations and then need to be redistributed. They're redistributed precisely by the grouping fields, and so that in the next stage, all of the resulting summary rows from this stage that have the same time and the same dimension values are always together in the next stage, and which is the group by post shuffle, that it now knows that the data is organized by this grouping field, so all of the values, all of the rows for a given set of time and dimensions will all be together, and therefore we can finalize the aggregate calculations and then apply ordering if needed during this stage. And finally redistribute again to whatever the next stage is. The limit stage applies limit offsets and limits, right? So we'll receive data from all of the workers, but we'll concentrate them in a single worker, and in that worker we'll be able to apply that final order by, the final sort, so that we can then take the particular set of rows starting at the specified offset and limited by the number of result rows specified in the limit. So something to take into account here is that if you're using a limit and an order by in an ingestion or in a SQL, you will need to make sure that there's not a large amount of data in the prior stage, right? Because if there is a significant amount of data in the prior stage that's all going to go to a single worker, we're losing parallelism here, and that will, if it's a very large set, will become a bottleneck, right? So something to be aware of. If you're using limit with order by, it's a good idea that the results prior to that are already summarized or are small in some form. In the final stage is the segment generator stage. So this will take the data that's been organized by time and by the clustered by dimensions from whatever the prior stage was. That's how they'll be reorganized into this stage, so that we can build segments in parallel across all workers, and build the segments from that data, apply the secondary partitioning, the time partitioning as specified by the SQL, create all of those columnarized and indexed segment files, and publish them to deep storage. And that's sort of it. Thank you.